All right, so I'm back again. I know you guys are probably tired of me and these videos. This is the only way I know how to break up the lecture. So I'm going to give you an example of a one-tail hypothesis test for a population mean when standard deviation is known. All right, so I'm using an example that's in your book, and this leads back to the example we talked about in the previous video with the 8,000 hours for a light bulb. So let's see. It says that the Edilite claims that its new CFL bulb has an average life that exceeds 8,000 hours. Suppose that the average life of a random sample of 36 of the new light bulbs is 8,120 hours, and assume that the population standard deviation for the life of a CFL bulb is 500 hours. All right, so we're going to use these steps that are described in your book to solve this problem for one-tail hypothesis test. So they've told us that they've taken a sample of 36 of these new bulbs, and that the average for the sample is 8,120 hours, and that the population has a standard deviation of 500 hours, right? So the first thing we're going to do, and I've already written it, is we're going to identify the null and the alternative, right? And so I'm going to now write with a different color pen because that will be helpful. So we know that the status quo, or the status quo was equal to the 8,000 hours. So currently we know that this light bulb has a lifespan of less than 8,000 hours, right? But the new, because it talks about Etta has a new light bulb, and the new, sorry, my handwriting is already bad, but it's super bad with this Apple pen. So we know that the new bulb is always the clue that this is the alternative, has a lifespan, they're saying, of greater than 8,000 hours. All right, so step number one, set up your null and your alternative. So your H naught and your H1. All right, step two is to give the value for the level of significance. Well, the level of significance is usually stated. So it says that level of significance represents the probability of making a type 1 error, right? So in this particular situation, they're setting the level of significance alpha is going to be equal to 0.05. And this is probability of a type 1 error. I did not go over type 1 and type 2 errors because I think it's pretty self-explanatory. You all can read that in your book. All right. So then step three is to determine the critical value. And a critical value is really your z-score. So the step three is to determine the critical value, which is the z-score. And also I'm going to draw your picture because I like to draw the pictures. I've been doing this for 30 years and I still draw pictures because it helps me be able to think about it logically. So if we're going to say, here we go. So here's our normal curve, and if this is mu, right? And if probability 0.05. So we know that the probability of the new bulb being, say this is greater than 8,000. This is our 8,000 right here. Let me just move this over. Here's our 8,000. Right, so probability of being over 8,000 is here. This is our 0.05 right there, and that's our alpha. All right, and then 0.95 chance that it's less than the 8,000. And then we know from looking up our z, the z of 0.05. And we know this just from doing this so many times and looking up the z-score associated with 0.05. This is the score is 1.645. So the z-score of 0.05 is 1.645. Step 3 is to calculate the appropriate test statistic, and our test statistic is now denoted by z of x bar, right? So we're going to find z of x bar the way that we've normally been finding it. Is going to be equal to x bar minus the mu of h naught over sample error, right? So this is going to be the 8,120 minus 8,000 over our 500 divided by the square root of 36. Because remember, this is now the divided by the square root of n. So this is going to end up giving us 120 divided by 83.33, and that is equal 1.44. So our test statistic is equal to 1.44. So now we're going to compare our test statistic with our critical value, right? So test statistic versus critical value. So that is the 1.44, and that is less than 1.645. So now, given that the comparison, we're going to look, there's a table in your book, and I have my book permanently folded to this page on, and I guess it's I don't know what page number it is. It's the table 9.3, and this is the upper tail test, right? This indicates it's the upper tail test. So for upper tail test, we know by looking in this book, upper tail test is that it describes it, the hypothesis. And I'm taking this directly from your book. The hypothesis is right, and in this scenario, it tells you that if the test statistic, so in this scenario, if you have this as your hypothesis statement, it tells you that if so it gives you two different scenarios. So if this is, so in our scenario, right, we are less than this particular scenario. If you compare the test statistic to the z-score, the test statistic is less than the z-score. And so in this particular situation, we do not, this is a do not reject. If it were this scenario, we would reject. So we are not rejecting H naught. So in terms of stating our conclusion, right? So we are saying that since we cannot reject H naught, what that means is you have to keep it, right? So because you can never say except, so you have to keep H naught, which means that the average life of the bulb is actually 8,000 hours or less. Status quo remains. So I hope this is helpful. I'm going to provide you another example as well. Contact me if you have any questions.